Okay, good morning everyone. We've got 3 sessions this morning. The first session is energy analysis at a conceptual level. The second session is energy analysis at a building level. And then in the third session, we're going to slightly jump back and look at conceptual modelling in Revit in terms of modelling conceptual building masses. Okay, so we've got quite a lot to cover. And just to recap, the emphasis of this course is about integrating energy modelling into the design process. So the techniques that we will be using today are about integrating the energy simulation into a design workflow. So it's quite important to understand the difference there. We're not looking at energy modelling simply in terms of analysing and producing data. We're looking at energy modelling in terms of how you can use that as a designer in a design workflow. So it's quite an important distinction. The kind of simulation and analysis that, for example, a building engineer may do may be more about producing the actual metrics, the actual data for the performance of the building. The analysis we will look at today, it will give you data, it will give you metrics, but the important thing is about how you would then use that in a design workflow. And in terms of aligning that with the assessment for this course, the case study makes you engage in that process, because the case study is not asking you to provide kind of precise metrics for the building. It's asking you to make informed decisions and to provide design advice as part of that scenario case study. Okay. So first of all, what is an energy model? And this is an Autodesk. No, sorry, this is an AIA, Architects, the American Institute of Architects slide, and they define an energy model in its simplest form as a set of inputs. Okay, and we're talking about building geometry, massing, system type, operation schedules. So in order to have an energy model, and to run a simulation, you have to have those inputs. Otherwise, how can the simulation energy know what parameters it is simulating? Okay, secondly is you need a calculation engine or a simulation engine. And this may seem a little bit surprising at first. There are a number of simulation engines available. So for example, Do2, Energy Plus, Apache Sim, and these are pieces of software that have been written that can analyze the energy performance of a building. Now the thing that sometimes is a little bit strange is the package, the software that you're using for simulation, whether that's Revit, whether that's Green Building Studio, IES, Vasari, Saphira, many packages out there. Those software packages are using one of these simulation engines. And when I first came across that, I always thought that was slightly odd, that Revit is not using Revit to simulate the building. In the case of Revit, it's using Do2 as a simulation engine. Now, as a designer, that all happens in the background, and you're not even aware that it's happening. But I've got a little chart later on in the presentation which will show you the simulation engines that are being used by the different softwares. And I think it's always important just to understand that those engines are running in the background. Okay, and then you need results or outputs. So you get data from the engine, and you need some form of understanding that data. So for example, performance comparison graphs, compliance reports, etc. So you need some filter, some way of understanding the data that comes out of the engine. Okay, the levels of modeling elements and inputs. So, the different kinds of inputs you need. Architectural massing and form. And in the most kind of basic simulation, you need a building shape and you need an orientation. You generally need to know what is the building function. Is it a school, or is it a residential building, or is it an office? The floor area, the number of floors, and the thermal zoning of floors. Now, what we mean by the thermal zoning of floors is within any building, different rooms, different floors have different thermal performance. So, for example, this room we would probably want at about 21, 22 degrees, but the toilets out there we probably would accept a much lower temperature because it has a different performance. Floor to floor height, floor to ceiling height. So all kind of fairly obvious, but these are the sort of architectural massing inputs that we need in the model. Then moving on to envelope. We need the information about the windows. Okay, windows play a very important role in energy simulation because glass is not a very good insulator, so we lose a lot of heat through windows, but also windows allow a lot of solar radiation into the building. So windows are very important in terms of energy in, energy out in buildings. And obviously shading is related to that. Wall, roof, foundation construction and makeup. So very important. What is the thermal performance of your roof, of your walls, of your floor? Interior partitions. Now you may think, why does it matter how an internal partition performs? It may not matter, but it would matter if we had different thermal zones on different sides of a partition, because then you would have energy transfer. Internal mass, so any thermal mass properties you have in the building from concrete floors, for example. And air infiltration is important. How much air is infiltrating from the outside into your building and vice versa. Okay, then we have internal loads. So, anticipated building occupancy. How many people do you expect to have in your building, and at what times of the day? You're all sat there, you're all giving out about 100 watts of heat each. Okay, I'm giving out a bit more because I'm standing up, because I'm working. You're just sitting there enjoying yourselves, maybe. But you're giving out about 100 watts, even just sat there. Okay. Lighting. Lights give out heat. Devices, computers give out heat. Interestingly, computers have got more and more heat efficient, so computers are not giving out as much heat anymore as they used to. Daylighting, elevators will use heat, will use electricity. Internal internal load schedules. So what we're talking about here is looking at the anticipated occupancy and looking at that prediction and what sort of heat and energy do we expect the occupants to use throughout the year. And then we move on to the HVAC, heating, ventilation, air conditioning, equipment and schedules. So the sort of heating system, the ventilation system, cooling system, if you have it, what are the sort of energy flows? What's the schedule of operation of those systems? Now, for our purposes as architectural designers, as building designers, as sort of people more involved with the kind of overall design of the building, we'll be less involved with the HVAC systems. We're not services engineers, so we're not particularly going to be specifying the boiler type. Okay, that's a bit beyond our remit. So let's have a little look at the currently available software. And as ever, software changes, so this will go out of date very, very quickly. But if you look down the left-hand side, you have a range of simulation software which is available. And Second column is the calculation engine. So as I mentioned, the actual software is not the same as the calculation engine. So for example, if we look at Energy Pro, here is using DO2. Okay. Revit, Vasari, Green Building Studio is using DO 2.2. And by comparison, IES, which is the other leading simulation package, is using Apache. Okay, so they're all using these different software engines in the background. And then the next column is talking about graphic interface. So is there a sort of front-end input? And what they're talking about here is how do you get that information into the software? And there are some softwares out there which have no kind of modeling inputs. You simply have to import the data from another package. But then other packages like Vasari, IES, you can actually model in the software. And as I'm sure you're aware, the emphasis in this module is about integrated design and simulation, which is why we are using the software where you can model directly in the software and perform the simulation in the software as well. Okay. Column here about is it appropriate for early design phase? So some of these softwares are much more kind of user-friendly. You can do very basic massing and you can test it. And that's what we look at in this session. Some of them, for example, Energy Pro, is a system which really it's more for kind of later design stages when you have more detail. Just in this column here, graphic results provided. Most of the software now will give you some kind of graphic output. Bar charts, pie charts, something that's sort of easy to read. But, for example, eQuest does not. It's a more kind of data-driven output. Now, second column from the end, is the software approved for code compliance modeling? So, what we're talking about there is, can you use this software to demonstrate compliance with your building code, depending on which country you're in and which building code you're complying with? And it's a mix. So, for example, IES, virtual environment, yes, you can use that to comply with various building codes around the world. Now, they remark here, Green Building Studio Vasari, they're saying it's not compliant for code modeling, but some of the later versions, actually, there is some compliance modeling in terms of LEED built in. Okay. Now, for our purposes here, we're kind of less concerned with code compliance, certainly in terms of design projects. Okay. But if you were working in a practice environment, you might be more interested in that. Freeware. Is the software free? Okay, some of it is, some of it isn't. Notice here, Vasari Green Building Studio, strictly speaking, it's not free. We just get it free because we have educational access. But if you were not having an educational license, you would be paying for it. Okay, you know, a lot of the good packages you have to pay for. You have to pay for the software in order to pay the people to make and to maintain that software. Okay, just a few units to bear in mind here. So we're talking about energy use intensity, and this is a very important metric in buildings. What we're talking about is how much energy does that building use per square meter per year. And it's a really good metric because you can use it to compare any two buildings anywhere in the world, any type of building. Okay? Because we're doing it by square meter, it doesn't matter how big that building is, the comparison is still valid. And the reason I've just given you these conversions here is because some of the different softwares are using different units. And depending on whether you're in the United States, whether you're in Europe, you might be using different units. Okay, so just to go through these units, a kilowatt hour, so that is the amount of, it's an energy unit, so that's the amount of energy you have by consuming a kilowatt of power for 1 hour in a building. And that is a commonly used unit of energy across all of Europe. Okay. Now, a kilo British thermal unit, we've mentioned before, is this slightly odd unit which is still used in the United States. And that's another unit of energy, but it's not a metric unit. So in Europe, we don't use that anymore, even though it's called a British thermal unit. Okay, and that's the conversion factor. A square meter to a square foot, quite obvious. In the United States, they're often still working in square feet, okay, but not in Europe. And then putting that all together, 1 kilowatt hour per square meter is 0.317 kilo British thermal units per square foot. So useful just to have those in mind whenever you're looking at a building. If you're looking at a project in America, they may well give you the figure in kilo British thermal units per square feet. And it's handy just to have that conversion factor in your head so you can compare. Equally, when you're looking at projects in Europe, more and more journals, more and more architectural books now will actually give you the energy use intensity of that building. And that's hugely important because you can immediately make that comparison in terms of performance. Okay, benchmarks. What we mean by benchmarks is, what are we aiming for? Okay, we're going to look at some energy. What are we aiming for? What's good performance? What's poor performance? What's excellent performance? And I've put this document TM46 onto Mole. And this is a document produced by CIBSE. Okay, CIBSE is the Chartered Institute of Building Services Engineers. So that's a UK institute who are they're at the forefront of building performance and engineering in the UK. And you can have a look at TM46 in your own time. And what TM46 is doing is it's defining some standards for buildings in the UK. So what are we aiming for in terms of performance? So really useful as a designer just to have a feel for what those performance benchmarks are. And I've just pulled out a few here. So a sort of target office, you would be aiming for about 95 kilowatt hours per square meter per annum. Fossil thermal, in other words, gas, 120 kilowatt hours per meter squared per annum. Carbon dioxide emissions, 75 kilograms of CO2 per square meter per annum. So that's the sort of benchmark figure coming out of that document. Now, you may aim a lot higher than that. So just to give you a comparison, this CO2 figure, in the UK, 2 or 3 years ago, when we were building schools to high standards, we were aiming for 15 kilograms of CO2 per square meter per year. So we were aiming for a huge improvement on that kind of benchmark. Okay. So that is that's the comparison figures for a school. And if we just go back, you notice that the figures for an office are much higher than a school. For electricity, it's much higher. For fossil thermal, it's slightly lower for an office. And that's because these buildings have different performances. So an office has higher lighting requirements, and an office will typically run for longer hours, 52 weeks of the year. Whereas a school, in the operation schedule, schools have holidays, schools finish at 3 o'clock, 4 o'clock. And in TM46, they're using a conversion factor to convert from energy into carbon dioxide emissions. Now this conversion factor does change all of the time. But the figure they were using, those are the figures they were using depending on whether you're talking about electricity or fossil thermal. And all they're doing is they're saying, on the whole, 1 kilowatt hour of electricity produces 0.55 kilograms of CO2. So, further references. This document, that's the link. You can download this document for free. And this is from the American Institute of Architects. And this is a very good document talking about integrated energy modeling in the design process. So that's kind of core reading. You really need to read that for this module. And what I've done here is I've just put some further references, some videos. These videos will go over the demonstration that we'll do in a moment. And these are Autodesk student videos, very good videos. Some of it will just be repeating what we're about to do. Some of it may add a slightly different level of analysis, and sometimes they may just perform the same operation but doing it in a slightly different way. So, I always find it really useful just to watch these videos, just see the kind of advice that's being given. Okay. So that was just to give you a sort of an overview and a background to what we mean by energy analysis and what we mean by conceptual energy analysis. Now we're going to move into Revit, and we'll start with conceptual analysis. We will stop at 10 to 11 and we'll have a break. We may not finish conceptual analysis before the break, in which case we'll just continue afterwards, and then we'll move into building analysis. Okay, so what we've got now is it's our same Arts Tower site, and we've now jumped to the stage where, there's our site, where we've actually now starting to look at some design options. So there's our site. This is available on Mole. There's our empty site, which you're all familiar with. Okay, and we're now in the position within our case study assignment where we're kind of imagining that some initial concept designs have been prepared for that site. Very basic, very quick designs. And we want to start assessing the energy performance of those designs. In the office environment, before we spend weeks and weeks and weeks developing them and working on the facades, we want to look at the basic shape, the orientation, the window configuration, and try and optimize the energy performance at this early stage. Right, so I'm going to show a few little techniques before we get into that. Okay, ZZ to zoom in. There's our model. I'm just going to switch off switch the sum path off for now. And ZE, zoom extents. You notice that the model is cropped. And I'll just talk through that process now. Some of you may have already found this if you were modeling your sites. You may have found this tool, but it's quite a useful tool in Revit. So, if we go into your view, you have this tool here called section box. Who's found this already? No one used section box yet? Okay. If I just switch that off, just give it a second. So there's our model. Okay, so we can see everything there. Just going to hide those lines. Okay, so there's our site that we're familiar with, and it's got the topo surface. It's got lots of buildings, but now that we want to start to look at this conceptual building in a bit more detail, we don't want to be constantly viewing this whole site. Okay, so this is quite a useful tool. If you click on, in your view, you click on the section box over here, it will just crop your model. It's only doing it as a view, so it's not actually, it's obviously not actually editing the geometry. And what it does is it brings up this section box. So this box that I've highlighted here. Okay, if I click on that box, I get these little arrows. Okay, and if I click and drag one of those little arrows, I can pull in this section box and I can start to crop my model down in the view. Okay, and what you find often is quite useful is if you go into a top view, you can do that slightly more accurately. Drag that in. Let's go to the end. So we've now cropped our model down, and we'll just drag the top down a bit as well. So we've got a bit less of the model to look at now. There's a bit less to regenerate. If I hit ZE, zoom extents, it will zoom just to that bit of cropped site. If you then, if you click on your crop box, your section box again, and you right click, you can hide in view. So you get a much sort of neater view of your model. The other thing you might notice is when you put a section box onto a topography, onto a topo surface, it will give you it will fill in the sides of that surface. So if you remember, when you just have the topo surface, it's like a paper thin surface. When you section box it, it actually looks like a thick base, which often in terms of when you want to output a rendered image, it just kind of looks better to have that thickness to the topo surface. Okay, so I've cropped our site there. Now if I just do WT Windows Tile, I'm just going to tidy up this other view quickly. Turn the sun off. Zoom in. And I'm just going to drag this section box to make it a bit smaller. Okay, WT Windows Tile, ZA Zoom All. And what you can see now is we've got these three different option buildings. Now this Revit file is available on Mole now. Okay, so in terms of you wanting to go start testing the energy, you can start playing around with this model. Now what I just want to quickly talk about is view options. And I'll do this quite quickly, but the video that I'm going to put on Mole today has a little bit more detail about view options. Okay, but the principle is we want to be able to consider multiple design options at this stage. And what we don't want to do is have lots of different Revit files. So obviously at this stage you could save as, and you could save as option A, option B, option C. But then all those different options are in different files. They're all taking up computer space, and you have to keep opening between two or three files. So there is a better way to do that in Revit, and it's called design options. So you need to go to the Manage tab up here, and then click on Design Options here. If I just drag that into the middle. And what it will let you do is it will let you create these different design options, and you can name them. as such. And the principle that Revit works on is you will put your basic site, anything which is constant, that would be the primary model. Okay, so that's the model element that is not going to change. So your site, your buildings, that will go into primary. Then, when you create new options, anything additional you can put into those distinct options. So, for example, option B, option C, option D, which I've got on the screen here, they're modeled in these different options. And it allows you to have all of those three different options in the same file, but you've got the ability to control, you can switch them off, switch them on, you can edit them without altering the other options. Okay. Now in this session, in the workshop at 12:10, I think it is, we're going to look in a lot more detail at actually how you start to create these conceptual buildings. So at the moment I'm just using the ones that I've created. But that workshop, we're going to look at a whole range of videos, and that's going to show you the capabilities in terms of conceptual massing. Okay, but for now we just want to use the one that we've got. Now the only other thing in terms of design options is within each view you have to set that design option. So if I maximize this view, ZE, zoom extents, VV gives you your visibility graphics for that view. And along the top, you have a design options tab. Click on that, and you have to actually set what do you want to see in that view. So although we know this is option C, you have to tell Revit to show you option C. So in here is where you just have to change your settings to tell it what to view. If you leave it on automatic, it will automatically show you the current design option. But I'm just going to leave it on option C because that's the option that we want to see in this view. Okay. WT, Windows tile, and we're back to our three views. Okay. What I've done here is we've got these, sorry, let's turn that around the other way. So we've got these three different conceptual buildings. And let's just look at one of them. Let's look at this one. Okay, so this is our option B. So there's our building that I've kind of made up. And if I just zoom in a bit, this is a conceptual building. Okay, so don't be confused by the windows. I have not sat down and defined these windows like this, because in terms of early stage design, all we're really interested in is amount of glazing, the kind of area of glazing, is it shaded, orientation. Because what we want to do is compare these design options. So you don't want, at a conceptual level, you don't want a hugely complex model. That's what we'll look at in the next session. Okay, if we go to our Massing and Site tab at the top here. Okay, I'm just going to hit Save actually, just in case. Okay, so under our Massing and Site, we've got some different view options here. Okay, so show mass by view settings. It will just use the default view settings that you have already created. Okay, so let's change the way that we're viewing it. show mass, form and floors. So all we're seeing now is the form and the floors. Okay. Now for any element in Revit, you can always override. So you can always click on that element and override its graphics. So for example, I've clicked on a building there. If you did just want to alter the appearance of that one building, if you right click, override graphics in view, you can always just modify that one element. So you have that level of control as well. But back to our view settings up here. Show mass surface types. And that's now brought back our windows, and it's showing our windows as a different color to our walls, and it's also showing the conceptual shading device. And the final one, show mass zones and shades. Shows the shading, shows the windows, but it doesn't show any different colors. Now I tend to find the surface types is kind of easiest to view. Okay, so we've got our 3 different conceptual buildings. So imagine you're in the office and your boss has said, okay, we've got these 3 designs, we're not sure which one we want to proceed with. I want you to do some energy analysis now to compare these different shape buildings. So if I just zoom out again. So we've got a long thin building, we've got this 3-story building, we've got a sort of, what was that, 5-6-story building here with a kind of angle on it. We've got this much longer, thinner building in a different position. So, we've got these different options that we want to explore in terms of shape, in terms of alignment on site. And before we absolutely fix those positions on site, before we fix those heights, the massing, let's compare the energy performance. So let's go back into let's start with our option B. Okay. Says our option B. And we now need to go into the Analyze tools. So there's Analyze tab along the top. Okay. Click on that. And because we haven't got much screen space, the energy tools are hidden under that button there. Okay. First thing you must do is enable the energy model. Now, mine's already done that. Okay. The first time you click on enable the energy model, Revit will need to sit and do a bit of work to convert your model into an energy model. Okay. I've already done it, so it won't need to do it now. Then, under this set of tools, you've got these 2 very important tools here. You have use conceptual mass mode or use building element mode. So these are the 2 different ways of analyzing energy. Are you analyzing conceptual mass, which yes we are for this session, or do you want to analyze a more detailed building model? Well, we'll look at that in the next session, but not for the moment, okay? So we'll leave that on the conceptual mass. And the next tool that we have is energy settings. So we'll click under that, and this is where we start to define our inputs in terms of building construction, building use. So let's have a look through the options here. So, building type. So you need to tell the software what kind of a building is this. Now for us it's a school or a university, so we'll leave it on that. And what Revit will then do is it will pull from its database a sort of predicted schedule of operation for a university building. And there are some assumptions in there, but broadly speaking, it will be about right. Location, we've already set because we set it when we were doing the solar analysis. But if that was not set, it would take you to the Internet Mapping Service again. I'm not going to do it now, but you can change your location. Okay. Okay. Ground plane. This is very important, and some people get this wrong. You need to tell the software where is the ground plane of your building. Anything below ground, Revit will use as a shading surface. So if you tell it the wrong level, it will not be calculating energy for those levels below ground. So just make sure you tell it the correct level, which I happen to know is level 10. Okay, if you can always rename these levels. You could rename level 10 to level 1 if you wanted, but I happen to know it's level 10, so we'll leave that set on level 10. Okay, export category. You notice here we're under the detailed model here. Now, for our conceptual massing, conceptual analysis, this actually doesn't make any difference because we're not working on a detailed model. So what I'll do, I'll leave those for now, and we'll talk about those settings when we look at the more detailed model later. Okay, looking at the energy model. Now, a lot of these settings you can leave alone. So, analytical space resolution. What it's talking about here is how detailed do you want the analysis to be. And 457.2 millimeters, this is because they're converting an imperial unit. So that I suspect is 1.5 feet from America. So what they're saying is, look, the rooms within your building, we're not really concerned with any more detail than 1.5 feet. Okay, we don't need to be modelling, every little bit of air in your building. That would be probably good enough. Generally, just leave that alone. Analytical surface resolution, again, about 300 millimeters. You can leave that alone. You don't want it to be trying to simulate down to such precise levels, or the software will just take forever. Okay, core offset. So, have a look at the building here. So look at my conceptual building here. You see that it has this core down the middle. Okay. At a conceptual level, Revit will put you a core in the middle. It will assume all buildings need to have a core with stairs and lifts and toilets in it. So it will put you that core in the middle. And at a conceptual level, that's fine. But what you can change is the core offset. So if I change that to 2000 and apply, just watch the building. Eventually. Come on. Okay, so the core, the offset is the distance from the facade to the core. So what I did there, I changed it from 3000 millimeters to 2000 millimeters. Let's go back into our energy settings. And I'm actually going to put that back to 3000. So, this is quite a small building we've got. If you're doing a bigger building, if you took this room, for example, we've got about 6 meters would be our core offset. So you can just set that. What it allows you to do is, even at this sort of basic level, is if you've got a whole range of spaces in the core that won't need the same level of heating, you can just make that bigger or smaller. Okay? Okay, back into our energy settings. Okay, you listening? You can divide the perimeter zones, and what it will do is it will divide up the building into north, south, east and west, and you have a degree of control then over those different zones. We're running out of time now, so I'll pick that up in the next session. Conceptual constructions, this is useful. What it is allowing you to do is you can edit the construction types of your conceptual building. So even though you haven't built walls out of bricks and insulation and plasterboard, you can still go into the settings here and make some changes. So for example, lightweight construction, no insulation, high mass construction, typical cold climate insulation. So depending where you are in the world, you can go in and make some basic amendments to the construction type. Okay, target percentage glazing. So how much glass do you think you want as a percentage of the facade? So if I just change that to 20%, keep an eye on the building. Okay, so it's shrunk all my windows down to 20%. It doesn't matter that, as I say, we're not saying those windows will look like that. We're just talking about the areas at this point. Okay, back into our energy settings. Target sill height. Where do you want your window sill to be? You can change that. Is the glazing shaded? Yes or no? And what depth is that shading? So if I just change that to 800 millimeters, again, keep an eye on the building. So our shading becomes deeper. Okay. Just go back into our settings, and then we'll finish in just a second. Target percentage skylights. If you had skylights, you can insert a figure here. We haven't got any at the moment. Let's just skip that. Building operation schedule. So what's the occupancy? Now if you leave it on default, it will extract an operating schedule from your building type. So normally you can just leave it on default, and it will then look at what building type are you simulating, and it will simply use a schedule appropriate for a university building. But if you want to change it, you can change it in here. Okay, different sort of throughout the year, different operation schedules. HVAC system. Now, there are some different heating ventilation systems in here, and I've put you a link on Mole. Where's it gone? Probably lost it. I've put you a link on Mole to some guidance about what those different systems mean. But I really feel for our purposes, we're not comparing different boiler types and different servicing types, because I think really that's something more for the engineers. What we're concerned with is building shape, building orientation, windows, shading, construction types. So I would encourage you not to really start simulating different boiler types, because I don't think it would mean a lot to most architectural designers. And at an early stage, conceptual level, I think the best thing is just to leave it the same for all of your different simulations. Okay, and then you're comparing the same system. But have a look, I won't go through it now, but you can have a look through this different guidance on the types of HVAC systems that you can use. Okay, we'll just finish off and then we'll have a break. And then the last setting, outdoor air information. So you can, if you want, you can change the ventilation rate in here, how much air are you providing to the occupants? 8 litres per second per person, or you can change it to air changes per hour. Again, normally you can just leave that alone. If you know what the correct figure is for a school, you can put that in. But generally, as long as you're using the same figure to compare your different designs, then it won't make any difference. Okay, so we've got all of our energy settings ready, and we'll have a break, and then when we come back after the break, we'll run the first energy simulation.